Alright, so today we are talking about symmetry. You guys should have a little bit of understanding what symmetry is already. Gonna test the week before Friday. I'll hang on during lunchtime.
Friday night more and then last week's work going to be on the test.
So that test you took was the last grade for quarter one.
No.
Everything you've been doing last week was on quarter two.
Wait, what?
So last week, starting from Monday, that was all considered to be quarter two. All that. The test we took just over a week ago, that was the last grade for quarter one.
Oh yeah, I knew that. You're
That started. And quarter two officially starts today. You're starting a new unit, so it doesn't make sense to put a new unit, half or a quarter of a unit on to the wrong quarter.
Yeah,
Okay. So you guys describe to me what symmetry is, or you symmetry? Mirror. See that? What else do you see symmetry? I'm pretty sure they're hermaphrodites, actually.
That means
Means they're both male and female.
that means like we're on side. That's class.
I don't know if it works out.
Smart. Keep going.
So back to symmetry. Where else have you guys seen symmetry? What is symmetry?
How was your day?
Things are symmetrical.
How was your day?
What's symmetrical?
When one side is
Sure.
Okay, so what's
Yeah.
that's like that?
a triangle. Equal angle.
Equal triangle has symmetry, yes. What else? Butterfly, that works. Some butterflies anyways. What? Show me one of those.
Yeah, actually, I kind of want to see that.
Yeah.
Look it up.
Maybe you're working back.
What?
Maybe you're working back one tick.
Yeah, right now. Right now. Right now. Nope, I can't go.
I think the easy example is your face is usually fairly symmetrical.
Okay. What if my face wrong?
Yeah, it might not be perfect, but it's close. Okay, but today we're going to talk about today we're going to talk about more specific types of symmetry, so we're going to learn the types of it. So, starting off, we're going to define symmetry. We're going to say a figure has symmetry if there is an isometry that maps the figure onto itself. What is an isometry? What's that? Yeah, the three image and the image are congruent. So one maps onto the other and it's the same image. So what you guys are most used to is going to be line symmetry. You draw a line through something, you fold it over, and it makes the same figure on top of itself. Perfect match. That would be considered an isometry. So we'll start off with line symmetry. That's what you're most used to. So a figure has line symmetry, or another word for line symmetry would be reflectional symmetry. So that's if there's a reflection over the figure's own image. That's where you draw a line that you basically split it into like two equal halves. You fold it over and it's perfect. So this here I have a parallelogram. If I split it in half, I'll just fold this piece over and fold perfectly onto the other piece. And our other type of symmetry we're talking about is rotational symmetry. So that means you can rotate a figure 180 degrees or less. Some things you can rotate more than 180 degrees, it's still the same figure, but that's not going to count for our definition. Our definition is going to be 180 degrees or less. So we said equilateral triangle has symmetry, it has line symmetry, which I think is probably what you're going for, is to draw a straight line here and map the two sides onto each other, and it's perfect. But then I can also rotate this triangle around. So if I rotate it under 20 degrees, I end up getting what looks to be the same triangle. I could flip it around again, but that would be 240 degrees, same triangle, but since it's more than 180 degrees, that doesn't count. So I can only say that has 120 degree rotational symmetry. And then there's a special case rotational symmetry where if it's exactly 180 degrees, we're also going to call that to be point symmetry. Got some examples of these. Let's look at line symmetry. Or even if this is scaling triangles, we can go with the same. None of the sides are the same. That's what you're going for. All these sides are different. So then if I was to try to draw a line, let's say you can try to draw a line there. Those two look the same. Not really. If I try to draw a line there, those halves don't really match up. If I try to draw that, it just doesn't work. So a scaling triangle would be a good example where you don't have any kind of line symmetry. There's no way I can split that in half to make two equal sides that pull onto each other. But isosceles triangle, which is one, and two congruent angles. So the angle and the sides are the same. So that one I can just draw a line right through the middle and it holds perfectly onto itself. So then if you look at a rectangle, do those two lines work? Yeah. I could fold this correctly lengthwise. So if you just look at a sheet of paper, fold it in half, hot dog style, what would you call that? Or I could do it the other way, hamburger style. Is there any other lines I could draw in there that might work? I think about maybe doing that. So if I drew diagonally, does that work? If I was to do that, just a map onto each other really nice. Oh, so that's what I got down here. If we try to do it diagonal, what ends up happening is we end up getting a corner that ends up being over. So even though they look the same, you have to be able to fold it directly across, and it has to be a direct match. Sure, I could cut it and rotate it, and then it would work, but just a straight reflection is not going to work at all. But when you talk about square, square has 4 equal sides. So that means no matter how you're going to fold it, if you do it diagonally, lengthwise, or widthwise, it will work. So that one, we're actually going to have the 3 lines of symmetry in that one. Then there are some special cases. A regular polygon is what we call a polygon that's got all sides are the same. So like a equilateral triangle would count 3 equal sides, square count 4 equal sides. This picture is a regular pentagon. I got 5 sides that are all the same. And we know that you can draw this, however many equal sides you have, there's going to be that many lines of symmetry. So if I have n sides that are congruent, then I'm going to end up having n lines of symmetry. So that's kind of handy thing just to know, just kind of check your work. Like if you're trying to find lines of symmetry through something like, say, a regular hexagon with 6 equal sides, you should be able to draw 6 lines through the lines of symmetry. When I talk about circles, I fold a circle, how many ways can I fold it to make it match onto itself? I can do it like straight up and down or straight across. I can do it diagonally one way, I can do it another way. Or I could choose any orientation I want. So circle, we're going to say there's infinite number of lines of symmetry. Because no matter how you orient your circle, there's always a way to fold it in half. Okay, so let's look at the case for point symmetry. So when I look at a parallelogram, that's just like a tilted rectangle. If I rotate that 180 degrees, so does that match my original figure? Yeah, so that works. Whenever you can rotate it 180 degrees, you have rotational symmetry. I think this rectangle. I do that, rotate 180 degrees, matches up my original figure. Versus, like equilateral triangles, we know these are symmetrical, but if I just do 180 degrees, if I turn around, it's going to end up having the point down instead of up, but it has to be a direct match. Even though I can hold it certain ways, it has to be exact match for it to work. So thinking about that, what letters of the alphabet do you guys think of that will have a point symmetry? H. That's a good one.
Capital I.
Capital I. O. T. So if I do T, that's still a T. No. Lowercase t. Lowercase t. Still not quite going to work. And T's are supposed to be a little bit higher than center. What else are X? X works. The others? Think of at least 2 more. T. I didn't try real nice. Z, if I rotate that, that still doesn't say C. I'll be drop symmetrical, it should work. Okay. So then when we're talking about rotational symmetry, our definition says it has to be 180 degrees or less, so I have to be able to rotate these. So if I rotate parallelogram, how many times can I rotate it to be less than 180 degrees and look at the same object? I'll do it 90 degrees, not quite the same. 180 degrees, that match up. So yeah, we can say that's got 180 degrees. How many times can I spin this equilateral triangle? 20, and is that it? I just did that 180. So that's 180, is that the same? No. So yeah, we're stuck with 120 in the triangle. What about a square? Okay, rotate that up. Yes, there's too quiet. What is that? 90. Rotate 90 degrees. Mine's so bad, Joe. Yeah. So square them, right? Rotate 90 degrees, rotate another 90 degrees. So square, 180 degrees. So square. As you said, 270 degrees. Is that right? What's the problem with 270? It's bigger than 180. So all we can say in that one is that this is going to be 90 and 180. Can't go further than that. This one was only 120. This one was only 180. Okay, what about how can I rotate that one with your rotational symmetry? You can't. See if I Make rotate that any way to get it to affect the original figure. Let's see if I can find a way to make it look like what we started. It's a little off. I drew that right. That's supposed to be about the same there. So that was a 72 degree rotation. Rotate again. That's a 144 degree rotation. Rotate again. That would be 216. So what rotations do I have in this? 72 and 144. Anything else? Nope. So it'd be an easy way to figure that out. What the degree of rotation is on that. Where's the 72 come from? Where's my 72 degrees coming from? How do we come up with that number? Look at this. How far around is the whole circle? 360. How many sides are in a pentagon? What's 360 divided by 5? 72. So if you have a regular shape divided by a number of sides, 360 divided by a number of sides, and that's going to tell you what each degree of rotation is. And you just got to figure out how many times you do that. It'll still be under 180. So let's look at these ones. I got looks to be a right triangle, probably right scalene. Does that have any kind of rotational symmetry? No. No way I can rotate it around and get the original figure. Stuff doesn't look like it. So we'll call that one a no. How about this rectangle? Does that have rotational symmetry? Is that 90? 180. 180, does that match up? Looks like it. That also has 180 degrees. Anything else on that one? Probably not. Okay, here we have a regular hexagon. Is that a rotational symmetry? Yeah. What kind of rotational symmetry is it then? Yeah, 360 divided by 60, or 360 divided by 6 is 60. Is that it? Just 60 degrees? No, what else can I do? 120. Anything else? 180. Okay. Then we have a parallelogram. Does that have any kind of rotational symmetry? 180. Let's turn all the way around. Looks like it. Anything else around? No. Alright. A couple more examples. So using the 3 different types of symmetries we've talked about so far, kind of symmetry does that look like that? Is that line symmetry? Can I draw a straight line through somewhere? So you can say, yeah, somewhere can I draw a line right down the middle? That match up. Twice. I think that's out. Any other kinds of line symmetry you guys can think of? No, probably not. Okay, how about rotational symmetry? Yes. What kind of rotational symmetry do we have? Okay, let's got 180. I agree that I can turn it all the way around to help be the same figure. Any others? These are all the same segments that's been split into, they're all identical. How many of them are there? 6. So I can spin it around. What kind of symmetries am I going to have? 60 and 120. So those are all rotational symmetries. And then if it has 180 degree rotational symmetry, it also has pen symmetry. This is the third one we talked about. Points. So it's basically saying if I have a center point that's equidistant to everywhere. Okay. Next one, okay, symmetry right there. Line going through where? Which middle? Horizontal, vertical?
This way.
Horizontal, so like that. That's good. Line. Whenever you're describing line symmetry, make sure you actually draw the line to show where the symmetry is. Any other kind of symmetries? No more lines. Any rotational? No, not really. Okay. How about third one? What do you see in that one? You see it? Line? Line going through where? Horizontally like that. It's not quite gonna work because this is smaller than that. So that's not gonna work. Diagonally, like from here.
No.
Like here.
No.
Is that what you're thinking? Yes. That's still not gonna work. And I'm gonna be flipping over like that. It's not gonna quite fit. I think maybe going like that.
There, that's what I said.
Up that. That gonna work. I think that's still not going to quite work. I think we'll end up getting a point out here because it's kind of like trying to cut across a rectangle. If you fold it across a diagonal, so it's still going to be pointing out a little bit. So this one, that's really close, but I think this one doesn't quite make it. Does that rotational symmetry? What kind? 180. Okay. Yeah, I can flip this around and it'll look the same. Any other kind of symmetry? Also, this point because it has 180 rotational. Yeah, what was the third one? Does it have any kind of line symmetry? Vertical? And horizontal? Those look the same? Yeah, I think so. I think we got two line symmetries. That kind of line symmetry? Yeah, this one, if you actually do the diagonal like this, it'll work because this is like perfect, but it's kind of like a square almost. But because each side is completely equidistant, you can draw two more lines in there like that. Okay, so you got 1, 2, 3, 4 different types of line symmetries in that one. Any rotational symmetry? I rotate this at all, get the same shape. Yeah. How far can I rotate it? 90 degrees, that's the same shape. So like it. Rotational. 90 degrees. Or 180 degrees. Anything else? Yeah, if we have 180 degrees, we also have points. Right, lastly, we can also expand symmetries into even more dimensions. So you can talk about 3 dimensions. So there's a couple different types we'll talk about for 3-dimensional symmetries. We can say 3-dimensional objects can have reflectional symmetry in a plane. So like if I have a perfect cube, I just drew a plane through it, like basically inserted a sheet of paper exactly through the middle of it. I can really rotate, I can really put this cube, the top half, onto the bottom half, and it's the same thing. So it works in 3 dimensions as well, like that. And I can also do rotational symmetry about a line. So rotating around the line. So like think a cylinder like a pop can, and you just drew a line straight through the center and just rotate about that line. It's kind of like infinite amounts of symmetry around it, because no matter how you turn it, it's going to work the same. So if we look at a couple of different objects that might be a little more difficult to look at. I think this also have any kind of symmetry is bold. Reflectional? What kind of reflectional? Where would I draw a plane? Like vertically?
Yeah.
And so let's draw a plane here. Or like kind of seeing this is going like into the bowl. The pack itself onto each other. Looks like it probably will. I think you can do that. Anything else? Rotational, where I draw the line, but back down the middle again. And if I would spin this around, but they go directly through the center, it's always going to look identical. So that works. Spin around that line. Okay. How about the base? Anything in that? So where would I draw a line? Down the handle. Are you thinking of rotational or reflectional? Reflectional, yeah. So I was to draw a plane that basically went right through the handle. I don't know really how to draw this. But imagine a plane that's kind of going directly through the handle, through the center of this, into the hollow portion of it. Think of it that way, it's going to split it exactly in half. It's going to kind of go right through there, split that in half. Like this line really going like inside of there, the plane's being inserted into it, the whole half are look the same. So yeah, so this one, say we have reflectional symmetry. So I have both the reflectional symmetry of plane, which abbreviates. And we also look at rotational symmetry. The line. On this one, we had reflectional symmetry. About a plane. And then, do we have any kind of rotational symmetry in this one? If I put a line through anywhere, can I spin it around and it looks identical? Really, the handle really kills us, and then the top and bottom aren't really congruent, so that's not really going to work too well for us. So yeah, it's just too asymmetrical for us to work like that. So all you can do is split directly through, slicing it basically right down the handle, right to the center of it. Make sure we're on the same page, then we'll want to go over the directions and these. So in the first set of problems, you're looking for the different types of symmetry. If it has line, make sure you draw the line, which puts them in the two halves. If it has rotational symmetry, tell me each of the angles that is being rotated about. Remember, you can't have numbers bigger than 180 for those. 19 to 22, make sure you sketch the figure and then draw lines. Don't worry about reflection or rotation on that one. We're just looking for line symmetry. 26, they're saying if I was to write math vertically like this, they're saying that I could do that. I could draw a line right to the center of that. and basically splits the word exactly in half. So one side of the word looks the same as the other side of the word. So find two more words that look like that. We split it right down the middle, and it looks the same on both sides. 32, you're looking at the same thing, but you're going horizontally. But draw a line horizontally through here. Everything looks the same, top and bottom. And you gotta make sure the equation comes true. Think about 10 over 10 is 1, 1 minus 1 is 0. 0 divided by 8, 0 leaves 1 divided by 0. 0 divided by 1 is 0. So that's 0 equals 0. So that's true. Make sure you have a true equation. And the inches about it. Yeah, the rest of it seems pretty straightforward. That question is pass. Pass that test for you guys. Yes, I'll pass those back to us.